So about the test number 3, you don't need to contact the DRC. I got something from the DRC. The test is at most an hour and 30 minutes. At most. If you are good, it should be done in 1 hour. I opened it for 3 hours because some people work, some people this, or some people that. It doesn't mean it's a 3 hours test. It's just to accommodate everyone because if I open it for 1 hour, people are going to complain. No, I can extend it to 11 p.m. Someone asked, that's fine. So it will be from 6 to 11 p.m. It should not take you more than an hour and a half if you're very carefully reviewing the questions. It's like an assignment that you take at home. So it's open notes and it's covering momentum and talks. Like I already posted everything that you need. Okay, so don't go contact the DRC because I told them no, there is nothing. You are not taking it at the DRC. I open it for 3 hours. That's plenty of time. I will be opening it for 4 hours. So you don't need a DRC, and you better not to miss it. So make sure you have your laptop. Don't use a phone in the bus or on the way to a friend or whatever. Use your laptop and the tablet. Otherwise, it can be hard. And make sure you don't have internet issue because otherwise the makeup is the next day, 8 a.m. in my office in person, on paper. So I'm warning you, don't miss it. Okay, that said, I hope everyone is fine. And I have extended the homework due last night. So if you need an extension, it's already done. We are almost done here. So last time we talked about the center of mass. So typical question, for example, for the pop quiz of today, you want to make sure that if you want something to be stable, you want to make sure that the center of mass is just above the base. Okay, otherwise it's not you're gonna fall. For example, in this case, and the center of mass is that point where the gravity is acting on. Okay, so that will be your center of mass. And then another thing I want to point out, so for example, in that case, he has a stable position because the center of mass here, okay, is just above the base. Okay, so this will be the base and the center of mass is just above it. And everything happens like the weight. So that will be the only force. And it's not the only force because you have the normal force pushing up, you have the weight pulling down, but the weight is always acting on the center of mass. So this is stable because the center of mass is above the base. This is unstable, right? So that means there is a torque. Why is this stable? Because the torque, when the force producing the torque is going through the axis of rotation, the torque equals 0. If the axis of rotation is here, you see that will be a non-zero torque. Is that clear? So if the force is going through the axis of rotation, there won't be any torque. Okay, so we talked about that last time. So the center of mass, okay, is responding only to the external forces. So in that case, she can manipulate her body around the center of mass, but the center of mass, when she's going to jump, is following a projectile motion, so a parabola. So in that case, it seems that he's hovering like horizontal, but the center of mass on its part is still doing a projectile motion. So you can manipulate your body around the center of mass. And that's what did this athlete here. You see, there is no way the center of mass could go above that distance. It will not be physically possible. However, you can manipulate your body. So the body will be above that bar here. Okay, so we talk about that. And that's, of course, that will not be making sense unless he was able to anchor himself. Okay, he had some kind of hook securing him to the ground, because the center of mass being here, the torque relative to the axis of rotation is not zero. So it cannot be an equilibrium unless you have a trick. Okay, so we talk about the center of mass. So you see, why is it that when you have a firework, you're going to have a display, this kind of display, because the center of mass here is at the center. So all the pieces here after the explosion have to rearrange themselves around the center of mass to make sure the center of mass is just going up and down, because it's going to be in free fall. So it's only listening to gravity, right? Okay, and just a short equation that we're going to use for the pop quiz. Nothing to be scared. It's very easy. So let's say you have two masses here. So that will be the center of mass. And that will be also the fulcrum. So if you put a fulcrum here at the center of mass, it's going to be in equilibrium, right? So the torque produced by the weight of this mass will be equals to the torque produced by that mass. Do you all agree? Okay, and that's how we define the center of mass. It's using torques. So here, again, let's say this is mass 1, this is mass 2. That distance here will be equals to R1. That distance here will be equals to R2. When there is equilibrium, we have M1 R1 equals M2 R2. And I told you that when you have equilibrium, you don't need to convert mass to kilograms. If it's in grams, you can keep it in grams. If it's in kilogram or Newton, you can keep it the same. So now if you take that equation here, which means there is an equilibrium, then if you have like here an x-axis here, and that will be the origin, and let's say here we have position x1, position x2, and here that will be the position of the center of mass, x, and then subscript will be cm, okay? I can manipulate, I can play with this equation with a little bit of algebra, and I can derive the following equation. The position of the center of mass, it's going to be the weighted average of the positions of each mass. So the equation will be, the position of the center of mass will be x1 m1 plus x2 m2 over m1 plus m2. Okay, so for the pop quiz, you're going to have to use that equation, but it's easy. It's very simple algebra. You can do the same thing using the weight. Okay, so you can say that the position of the center of mass will be equals to x sub 1, the position of mass 1, times the weight of 1, plus x2 times the weight of 2, over weight 1 plus weight 2. It's the same thing. So all those three equations are the same. So the equation for the center of mass to find its position comes from equilibrium. Is that clear? And of course here you have a big weight, and here you have a small weight, and here you have the normal force from the fulcrum. Let's say you have a fulcrum here, but the torque produced by the normal force equals 0 because it's going through the fulcrum. Does it make sense? Mm-hmm. Okay, if you have a door and you push, when you push on the hinge, nothing will happen. Any question? That's a simple equation. And remember to use your textbook. Okay. So for example, if you have like a missile for fun, And you see, it's going to start. It has some initial velocity. So it wants to follow a projectile motion because it's in free fall. But in the meantime, here you have an explosion. Okay, the center of mass will keep following the same trajectory because it's only responding to gravity. So the center of mass will keep going over that parabola, and all the little pieces will rearrange themselves in such a way that the center of mass will follow that projectile motion. Isn't that interesting? So it's studied a lot in the science of explosion, for example. Okay, so any question? Okay, so we start a new unit. So that new unit is not going to be for the test. For the test, I already have posted an announcement, so make sure you go over my announcement. Again, it's going to be Tuesday. We do have class on Tuesday. Making this clear. And the test I will open from 6 to 11. It doesn't mean that it takes that all time. I'm trying to accommodate everyone. And don't miss it. So because I wake up at 4 a.m. every day, so I don't care coming here at 8 a.m. But maybe you care. So we're going to talk about work and energy. Okay, so it's a new unit. And so some units for energy, you have the joule. Okay, you already know that because when you are taking a chemistry class or you study thermodynamics, talk about energy. This is another unit of energy that we never use. It's a very, very small unit of energy. You have the chemical, like the chemistry, the calorie that you use in chemistry. So that will be with a lower case. It's about 4 joules. And you have the food calorie with uppercase. So the food calorie is 1,000 chemistry calories. So just to give you an idea how much energy we have in food. So if you eat like one cookie, the cookie is 150 calories, it really means 150 kilocalories. So that will be 150 times 4,000 joules. And then another unit will be kilowatt hour. So we'll talk about that. Okay. You have different forms of energy. I'm sure you are aware of them. You have kinetic energy. So that will be the energy of motion. You have energy in radiation, in light. So for example, UV light can burn you, or just light, you can get a sunburn. So that means radiation carries energy from the sun to us. And then you have potential energy stored. So for example, in fossil fuel, that will be potential energy waiting to be released, right? To be burned. The fat that we have is also potential energy, chemical potential energy, and that will be gravitational potential energy. Okay, so we'll talk about that in more details. So let's talk about kinetic energy, because it's always a question for the pop quiz or maybe the final. Kinetic energy, of course, it depends on the mass. It makes sense. If someone knock you over, it's going to be worse if it's a child or if it's someone very heavy. So it will be proportional to the mass, but it will be proportional to the speed square. So always conceptual question about that. What does it mean? It means like if you go 30 miles per hour and you increase your speed to 60 miles per hour, so the speed is multiplied by 2, very good. Mm-hmm. But what is the square of 2? 4. The kinetic energy will be multiplied by 4. So it's worse. Yes, it's worse to double. Yes, exactly. If you double the mass of the car, It's not as bad as doubling your speed. Exactly. But it also means that if you double your speed, okay, so you multiply by 4 the energy, but all that energy, when you're going to hit the brake, it means that it will take 4 times more distance to stop the car. So faster you go, larger is the distance between you and the car in front. Because more kinetic energy you have, more distance it will take to stop the car. So if you multiply the speed by 3, the kinetic energy will be multiplied by 9. So that's why kinetic energy is very deadly. That's what killed the dinosaurs 65 million years ago, because the meteorite far away from the Earth had potential energy. All that potential energy turned into kinetic energy, and when it's going to hit the Earth, all that energy, huge energy, is released. So the Earth was taken to a broil and destroying everything. And it was like a nuclear winter. So it was very bad. So anyway, that's the idea of kinetic energy. So kinetic energy is 1/2 the mass times the speed squared. And here it looks like it's a vector. It's not. We don't have to worry about components. You take the speed and you square it. Yes.
I read somewhere that hypothetically, if a grain of sand were to hit Earth at the speed of light, it'll just
Yes. So if like the story, I didn't hear about the sand, but like if you are on top of the Empire State Building and you drop a penny, and then if there is no air resistance, it can kill you, right? Because it's gonna get so much speed. You square it, all that energy is gonna go into you. It's gonna deliver that energy. So let's do some easy numerical examples. So, okay, let me define. So again, it's easier, right? You pass the cap of kinematics. Kinematics is the most challenging part. So let me define those. So the first uh, physical quantity, new physical quantity, is going to be kinetic energy. Kinetic energy will be 0.5 or 1/2 times the mass times the speed. Okay, even though usually the notation is v, but it's really the speed. So we don't care about components, it's just the speed square. The unit for kinetic energy will be the joule. The unit for mass is the kilogram, and unit for speed will be meter per second. Now, what we call a change. So you remember, it's a little bit like the change in momentum is the final momentum minus initial momentum. So remember that for test number 3, a change in momentum, final minus initial. So the change in kinetic energy will be 0.5 times the mass. And then you have, okay, I'm going to write it down, the final square, speed square minus the initial, right? So that will be the final kinetic energy, and that will be the initial kinetic energy. So if I factor out, so if you factor out this and that, you can write it down on your own. That's going to be 0.5 the mass V final square minus V initial square. Because sometimes a typical mistake will be V final minus V initial square. No. It's a final speed square minus initial speed square. And then you have the 0.5 times the mass. Okay? Likewise, remember for the test, change in momentum is the mass times the final velocity. So in that case, it's a vector, so it could be positive or negative initial. It's not the same. Here we have magnitude, and here we have a vector, so velocity can be negative or positive. For the kinetic energy, it's only the magnitude. So we don't care about the sign. But when you're going to do test number 3, remember, first thing you do, right is plus and left is minus. Okay? So anyway, number 1. So you have a 50 kilogram. So that will be the mass, initial velocity, or initial speed, I should say. And that will be the final speed. Okay? So plugging in. What is the change in kinetic energy? So you 0.5, the mass, final speed square minus initial speed square. You just plug it in, right? So it's going to be 0.5, the mass, and here you have 5 square, and the final is 0, minus 5 square. So it's going to be 25 times 25. 625, but it's negative 625 joules, meaning energy was lost. How did it get lost? Because there was a force applied during that time, and I guess that will be friction. It hit the brake. Okay? So it's not that hard. So let's move to the next one. Don't wait for me, okay? Just do the next one. So the mass here, and that will be the velocity. So just asking you, what's the kinetic energy? So the 0.5, 40, and then 10 square. What did you get? 2250 joules. Do you all agree? So you do PET 45 times 100, and then you divide by 2, okay? Did you all do it? And then I'm going to call that kinetic 1. And then kinetic 2. Now the speed is half. So what's going to happen to the kinetic energy? If you divide the speed by 2, the kinetic energy is going to be divided by 4. 4. Very good. Now you can verify it. Okay, you can verify. So 0.5, 45, and then 5 square. And you're going to get, right? So 2250, yes. You write 562.5 joule, yes? And if you do speed 1 over speed 2, you're going to get 10 over 5, it's going to be 2. But if you do kinetic energy 1 over kinetic energy 2, you're going to get 4. So when the speed increases by a factor of 6, kinetic energy will increase by a factor of 36, because kinetic energy is proportional to the speed square. Okay? So that way, like I can have conceptual question, and I can say, okay, someone is going at 30 miles per hour. I don't know, kinetic energy is 5,000 joules. What's gonna be the new kinetic energy if the speed is 15. So because here you divide by 2, yes, so here it's going to be divided by 4. And that way you don't need to do the computation. So typical conceptual equation. Okay? However, for the mass, it's going to be proportional. So if the mass is divided by 2, kinetic energy is divided by 2. Okay? So let's see what's coming next. Okay, so about thermal energy, because I know many of you maybe take the MCAT or so you or are going to take thermodynamics. So in physics, actually, the real definition of temperature is not how hot or how cold something is. It has a defined definition. The temperature is the average kinetic energy per particle. So it means, for example, if a system has a large temperature, it means those particles are moving really fast. They're going to jingle and shake really fast. So each one of them, they're going to have the same kinetic energy, but large kinetic energy. If you take the same system and you decrease the temperature, the kinetic energy per particle will be smaller. And there is an equation for that. So the definition of temperature is actually the kinetic energy per particle inside the system. So if you have a gas, you increase the temperature, the gas molecules are going to move faster, they're going to have more kinetic energy. And if you touch something very hot, let's say this is very hot here, right? And this is all those molecules are moving really, really, really fast. I touch that, what's going to happen? The molecules of my finger, they want to join the party, right? They say, oh, they're having fun here. I want to join the party. So they want to move also really fast. I'm going to destroy my skin, and then there will be a message sent to my brain and remove your hand, dummy. So I remove my hand. Right? But that's the idea, because all those molecules, they are bouncing off my fingers. So all those molecules here wants to move also really fast. So that's the real definition for temperature. But what we call thermal energy, that will be the total amount of kinetic energy inside the system. Okay? So it means, like here, you have an oven, 400 Fahrenheit, and here you have boiling water, 210 Fahrenheit, just as it's going to turn into steam. So which one will have the largest kinetic energy per particle? The oven, right? Because it's the temperature is larger, so each particle has more kinetic energy than this one. However, do you rather stick your hand in the oven or in the boiling water? Oven, right? When you're making a cake, chocolate cake, it's no problem. You're not going to burn yourself. Why is that? Even though the particles are moving faster, you're not going to have many of them. So when you put your hand, they're going to bounce off your hand, but it's not going to destroy your skin. If you have many of them bumping into your skin, all the molecules here, they get the energy. You have energy being transferred, and they also want to move really fast. So don't confuse. Temperature will be the kinetic energy per particle, but the thermal energy will be, it depends on the density. Okay, and so we have kinetic energy, we have thermal energy, we have energy contained into radiation, so radiative energy. And here we're going to work with potential energy. So potential energy is energy stored that is waiting to be released. Example, if you have a notebook here, right? It's not doing anything. It's just standing there above the table. but it has gravitational potential energy. So if I let go, all that potential energy is going to turn into kinetic energy. But if so I let go down, and then I place it back here, it's going to still have the same potential energy. Okay, so this is called gravitational potential energy. So we're going to see that the equation for gravitational potential energy is very simple. On Earth, so G is going to be 10. So it depends on three things. Do you have you put your hand here. Will it be the same thing if you have like something like a bowling ball or a tennis ball? Definitely a tennis ball, right? So the potential energy, how much damage it can do to your hand, depends on the mass. Because it goes from potential to kinetic, and then it's going to go into your hand. It's going to apply a force over a distance, and you can break your bones. So it depends on the mass. What else does it depend on? Gravity, okay? So if you are on Jupiter, the acceleration will be larger. So the speed that it's going to reach will be larger. So it's going to hurt more. So it depends on gravity, the acceleration due to gravity. And it depends on the height. The higher, worse it gets. So the change in potential energy depends on the mass in kilogram, depends on gravity, which is 10 on Earth, and depends on the height in meters. So for potential energy, we always talk about the change in potential energy. Okay? So in that case, it would be delta H. And then we're going to touch on that, but not too much. You have also elastic potential energy. So for example, if you're doing exercise, Pilates, if you're taking a Pilates class, they like to work with those bands, right? So when you stretch the band, you are storing elastic potential energy into the band. And if you let go, what's going to happen to the potential energy? Kinetic. Release to kinetic energy, right? But you have to do work on it. You need to apply a force over a distance. You store elastic potential energy, and that goes to kinetic. Another example is chemical potential energy that we store in fat, sadly. So this is called chemical potential energy because if I exercise a lot, I can burn that, I can release that energy that will turn into water and CO2 and energy. Okay, there is, and if you listen how it works, at the end is only about physics, because at the end it's a transfer of electrons from the mitochondria to the water, and during that process, energy is being released. So each time you are burning fuel, it could be fossil fuel or it could be fat. Okay, you're gonna release energy, you're gonna produce water and CO2. So in biology, you learn that the currency for energy is ATP or something like that in the phosphate bonds, whatever. But at the end, you are breaking bonds and you are releasing potential energy. Okay, so here, you're gonna go more simple than that. So the unit for potential energy is in joules. And you decide where is your potential energy equals to 0. So is it the ground or is it the table, for example? So the change in potential energy will be mg delta h. Okay, so let's stop talking, do it. So potential energy is always relative to something. So first thing you always draw. Make a drawing, and more you do here, and less you have to do at home. Okay, don't give me the answer right away. Wait. So we have a ground level, and this is a table. Can you see that it's a table? Okay. And you have a break here. And what else is given? That height here is 0.5, and this is 1 meters relative to. So potential energy is mg times the height. So if you are asked to find the potential energy relative to the table, okay, so you're going to say, okay, I'm going to decide here the potential energy equals 0. And I want to find out what's the potential energy here. Or you can say, if you want, you can say that the change in potential energy equals mg delta h. Okay, and that mass is 3 kilo. So you see, we should start with that. Like kinematics should be saved for later because it's not easy. So potential energy, it's always relative to something. So relative to the table, it's going to be what? What's the mass? Times 10 times 0.5. So what do you get? 15 joules. Do you all agree? Everyone? Yeah. So then it's always relative to what? Okay, relative to the ground. It's going to be 45, so it's going to be the mass, 3 times 10 times relative to the ground. It's the height is 1.5. So relative to. So 1.5, and you're going to get 45 joules. So potential energy is proportional to height. Why does it matter? Because if you put your an egg, I don't know what can we put? A cockroach. Okay, I don't like cockroach. If you put a cockroach here, or if you put a cockroach there, you see the consequence will not be the same because you're gonna have more kinetic energy. Okay, and kinetic energy will go into force over a distance. So you can think of energy as the ability to destroy, to do damage, to go into, to apply a force over a distance. How do I know it's going to be over a distance? Because that thing goes from that to be totally flat. So there is a force over a distance. And it will be worse here than it is there. So the reference level does matter. Any question? Okay. So I have introduced a lot of physical quantities. So far, we have kinetic energy, we have potential energy, and now I'm going to introduce yet another physical quantity that is not the same as the one that you use in everyday life. That physical quantity is called work. And in physics, it has a different meaning. So work is the amount of energy in transfer. Okay? So work is energy in transfer. And it's a new physical quantity. Okay, and it has a definition, but let me explain. Let's say, for example, you're gonna pull like a wagon here, and maybe okay, you're pushing that. You have your knees inside. Okay, so you're applying a force. Okay, so that will I should be putting my force here, right? Okay, so you're pushing. So that's a push. That will be your applied force. Okay, it's a vector. And now there is no friction, say. So it's going to move from here to there. So that will be your displacement. Okay, remember displacement, final position minus initial position. So that cart here, it's going to move from position 1 to position 2. So you're going to push, what's going to happen to the cart if there is no friction? But is it moving at a constant speed if there is no friction? Accelerate, because F equals ma. So it's going to move faster. So let's say it was not moving to begin with, right? So here you're going to have a final speed. Do you agree? Right? So it's going to speed up. What happened? There was a transfer of energy from you to the system. Okay, there is energy transfer from you to that system here. That transfer of energy, that's what we call the work. And that work turns into kinetic energy. Okay, so there is work done. So we're going to say there will be done work by you on the cart here. That will be how much energy is being transferred from you to the cart. And that will be used to increase the kinetic energy. Does it make sense? So what can I say? So let's say you start from initial velocity and to a final velocity. So that work done will be used to increase the velocity. So increase the kinetic energy. So the work done by you on the cart will be equals to the change in kinetic energy. Okay? So let me ask you something from kinematics. What will make it go faster? More force, very good. If you push harder for the same distance, it's gonna move faster. Does it make sense? Mm-hmm. What else? So the mass. In that case, like for the same mass, of course, it will have more inertia if the mass increases. But in that case, the mass does not change. What else can I change? So okay, we neglect friction. I just want how much energy is being transferred. If I want to make it faster, like if you push something, like if someone is on a skateboard, you push over a small distance versus you push that person over a large distance. So it will be time, but in that case, time is distance. It depends on the distance. Yeah, you can do those experiments on your own, right? Someone is on a skateboard, you make a mark, you push that person over, I don't know, 3 yards, see how fast that person is going, and then you do the same experiment, but you push with the same force over a distance like 4 times. Like 4 times 3, 12 yards. And that person should go faster. That's all experiment you can do on your own, right? For the same force, for the same friction. So it depends on the distance. So in physics or in science, all you have to do is to multiply. So the work done by you on the cart, if you want to have a transfer of energy from you to the cart, you need to apply a force. But let's say now the cart is not moving. Let's say you put a stone here. Is it going to move? Are you increasing the kinetic energy? No. So you are pushing and sweating, so but you are doing work on the environment because you are getting hot and all those molecules around you are going to move faster, but you are not transferring your energy to the cart. So it has to be over a distance. So the work done by you on the cart will be the applied force times the displacement. That's a scalar. Okay, so it's a scalar. That here we take the magnitude and here we take the magnitude. So the amount of energy being transferred from system 1 to system 2 is the force times the distance. Is that clear? Mm-hmm. Where is that going? It will be gone to kinetic energy, to increasing the kinetic energy. Okay? So we have a new physical quantity which is called work, and work is force applied times the distance the force is applied through. So, for example, these guys, and we, of course, you're gonna have friction, but we are not talking about the work done by friction. We are only talking about the work done, the transfer of energy between you and the crate. So if you are applying a force 100 Newton and the displacement is 10 meters, what's going to be the energy transfer? 1000 joules. You all agree? You multiply the force by the distance. And where is that 1000 joules going? Into increasing the kinetic energy of the crate. The crate is going to move faster. And you already know that because in kinematics, not in kinematics like Newton's second law, F equals ma, if there is a force, there is an acceleration. Okay? Now let's go back to my example here. Now, what's going to happen if there is friction? So some, not all of it, but some of the energy gain will be lost into heat, which means that kinetic friction is also doing work, but it's taking energy away. Okay, it's like a debit. This is a deposit, that's the withdrawal. It's taking energy away. So that energy will be positive and it goes to kinetic energy. And when friction is doing work, okay, it's doing negative work. It's taking energy away. So the work done by friction on the cart will be equals negative the force of friction times the displacement. So friction is taking away. So it's like you have a bank deposit. So when work is positive, you are putting money in your bank account. And when friction is doing work, you are taking away. Is that clear? Okay. So work is not a vector, it's a scalar. Okay. And work is negative if energy is removed from the system, and work is positive if energy is added to the system. Okay. So taking to thermodynamics, for example, here when you are pushing here like a pump, and what's going to happen to the gas? It's going to be, so you push down. What's going to happen to the temperature? It's going to increase, right? Like if you have a bike and you pump it up, pump it up, pump it up, it's going to be hot. You know the pump. So here you increase the temperature because you did work on the system, and that work, okay, was increasing the thermal energy of the system. So all those little molecules inside, they're going to gain kinetic energy. Okay, so they're going to move faster, and that will increase the thermal energy. So so think about that. 2 seconds. Okay, don't say anything yet, but think about that. 2 seconds. So now you have two forces acting on the crate. So it's like a free body diagram. 100 Newton you push over 10 meters, but you have a frictional force, or kinetic friction, opposing the motion, which is 50 Newton, but to the left. Okay, so what is the work done by you? So this is you on the crate. What's going to be the work done? How much energy you are burning? So it's going to be, yes, 100 times 10. Do you all agree? Okay, so it will be 1000 joule. So energy is transmitted, okay, transfer. So it's energy in transfer from you to the crate. Okay? And then what about the work done by friction? So the work done by friction on the crate, it's going to be that. Thank you. It's going to be what? Very good. Excellent. Very good. So when you balance, what's the balance? What's the net work? Plus 500. So it's still a gain. It's still a gain, but not as much as if there was no friction. So the energy level, it's like a level, right? So the energy level of the system will increase by 500. It's like a gauge, right? It's going to increase by 5,000, and that will go into increasing the kinetic energy of the system. It's still going to move faster. What do you think is going to happen if you have a frictional force of 100? So it's going to move. It's going to move. Let's say you make it move at a constant speed. So it's moving at a constant speed, but is the speed changing? No. So it can have kinetic energy, but there is no change in kinetic energy. So what matters is the change in kinetic energy. So if it doesn't go faster or if it doesn't go slower, right, that means no work is done. Of course, we forgot you also have up, you're going to have the normal force, and down you have the weight. But are these forces doing any work? Do they help making it going faster or making it go slower? No. So we say the work done is 0. So the work done by the normal force is 0. The work done by the weight is 0. They don't help. And how do we know usually that no work is done is when the force is perpendicular to the displacement. There is no work done because they don't help changing the speed. Work is done only if it can change the speed. Is that clear? Mm-hmm. So the definition will be the work done by a force on a system will be equals to the force parallel to the displacement. Let's say displacement is along delta x. We want the component only parallel to the displacement. If it's perpendicular, there is no work done. It doesn't help. Agree? Okay, so sometimes it's not intuitive. So, for example, if I'm okay, so if I'm holding this, and this is very heavy. Oh, okay, that's better. So it's very heavy. I'm getting tired. But am I doing work on the system? No, because I'm not helping it going faster or slower, right? So I'm not doing work. Even though I'm getting very tired and I'm sweating, it's hot. I'm doing work on the environment, right? All those molecules around me are going to move faster, but not this one. Now, if I move at a constant speed, am I doing work on it? No. The force is perpendicular to the displacement. Perpendicular to this displacement, no work is done. Now, if I start to run, then there will be a component parallel to displacement. So yes, then I'm going to do work. So if a force is perpendicular to the displacement, there is no work done. Okay, so let's see. Okay, so let's do this one. So we are focusing on this crate here. So you see, I have a crate. It's on the truck. And do you remember in physics, it all depends on the system you are putting in your imaginary bag. Okay, it depends what are you interested in. I'm only interested in that crate here, and it doesn't slide. So if it does not slide, that means there is a force, right? So the truck is accelerating and the crate is accelerating with it. How come it doesn't slide? What is the force that prevents things from sliding? But what type of friction? Static friction. So static friction always opposes sliding. So he wants to slide this way, that will be static friction. Agree? Okay, so from here, we're just gonna use the same methodology. And your textbook is very nice, Johnson and Cudnell, so make sure to do the solve problem. Okay, so you have three forces acting on that crate, and you have the acceleration. So acceleration here is 1.5 meter per second square. And you have the mass. The mass here is 120 kilogram. And displacement, so the crate is moving with the truck, and the displacement is 65 meters. So first of all, let's find the force. How can I find the force using Newton's second law? Yes, F equals ma, exactly. Okay, so you see the normal force is balancing out the weight. So we don't care about that. Up equals down. The only unbalanced force is the static friction. That's the force that makes acceleration happen. Remember that if there is an acceleration, there is a net force. And the net force is this force. There is no other force. This one and this one, they kill each other out. So that will be the mass times 1.5, which is 180 Newton. Agree? Yeah. So then you just apply the work. The definition of work will be the force applied on the crate. And the static friction is just transmitting the work done by the engine, the fossil fuel that you are burning. So you just apply the definition, it's just force times displacement. Okay? So by definition, the work is always force times displacement, and the force has to be parallel to the displacement. So that will be, do we have the force? Yes, and the displacement 65. Right. Yes. 11,700 joules. Okay? And if you have that, you can find the increase in kinetic energy. Yes. No. Yes, stays on. It's a little bit confusing because what's happening is that the static force is here. Make it otherwise if there is no static force because of inertia, so the crate will stay at the same place and the truck will move away from the crate, right? So it will move this way and the crate will stay there and it's going to fall. You see that a lot on the highway if you don't secure that. So this is not very safe. Boom. Right? And why is the static friction is doing work? You might think, okay, it has no energy, but it's doing work because it's just a way to transfer the work done by the engine on the crate. So that's where the energy comes from. It's just the engine. Okay, what about here? So remember components of forces. So a force comes into components. So if you have a pull, 50 Newton, you can find the X component and the Y component. And they have different jobs. Only the X component is providing the acceleration, making the crate moving faster. The Y component is just lifting off the ground and then teaming up with the normal force to balance out the weight. So you have less friction. So if I want to find what's going to be the work done by the pull on the crate, what is it that I need to use? Do I use the 40 Newton, the 50 Newton, or the 30 Newton? 30. Okay, only the X component is helping it going faster, trying to change the speed. The Y component is just lifting it. So it's not involved in changing the kinetic energy. So work is done by a component or by a force only if kinetic energy could change. Sometimes it cannot change because you have friction. But if there is no friction, yes, it's going to work, right? Because remember, you're going to have an acceleration, F equals ma. So in that case, the speed will change. Agree? Mm-hmm. Okay, so you're going to have, in that case, so what's going to be the work done by you on the crate? So the work done by the pull on the crate will be equals to the, yes, so the 30 Newton, okay, because that's the only component that is helping. So 30 times, what's going to be the displacement? 10. So that will be 300 joules. So what's going on? You are burning fuel, all those chocolate cookies, and energy is transferred from you to the crate. So the energy level of the crate is going to increase and the kinetic energy is going to increase. Any question? Okay, let's try to do this one. It's a little bit of components, so at least there is a one to have done so many components and vectors. I took that from somewhere, so I think it's a nice drawing because you see all the grass. So remember, a force has components. You go from the tail. That's the tail. That's the head. The head is gonna be the X and Y. Do you remember that? Mm-hmm. So I cannot see anything. Where is my 60 degrees here? Here, that's 60 degrees. So this is 60 degrees. Okay, I'm gonna draw the force here because it's hard to see. So you have a vector here, okay? It's 20 Newton, so that will be the magnitude. And that angle here is 60 degrees. And so it has two components. Remember, the head is the component. So it has a X component here, and it has a Y component. And that will be your displacement. So which one is doing the work? Which one makes the acceleration happen? X, we all agree with that, right? And we only worry about the magnitude. So here, what do we use? You have a right angle triangle. So the X component here, you see, this is the hypotenuse. That will be your angle. So that side here is what? Adjacent. So it means I'm going to use cosine. Okay, so the work done by the little boy, I don't know, to the system here will be equals to the X component times the displacement. And this is in magnitude. And the work is positive because you increase the speed. So that will be, what is the force? 20. So 20 times cosine 60 times 150. Cosine 60 is 0.5. So 0.5 times 20 is 10. It's 15 joules. Okay? So that will be how much work is done by little boy on the system. Okay? So let's do this one. Okay, more you do here, let's you have to work. Yes. Okay. So that comes from your book. If you have the Johnson and Cutnell, which is a very nice book, especially if you want to be in a medical field, exercise science, biology, things like this, chemistry. It's a very nice book. And so that comes from that book. Okay, so pulling, but it makes an angle. So which which component of the force is producing the acceleration. That will be again X component. Very good. Okay, so the work done by the lady on the suitcase will be equals to, so that's going to be the force 45 times the cosine times the displacement. 2170. Yeah. Do you all agree? Yeah. Joules. And you have, of course, you're going to have wheels to decrease the friction, right? Mm. Okay, so this is an interesting example to understand. If you lift what is called a dumbbell,
Barbell.
Barbell. Okay, so if you lift the barbell, you are doing work against what? Gravity. So gravity is trying to slow it down, and you try to speeding up. So the work done by you on the barbell will be the force applied times the distance, right? But the work done by gravity, if it's moving at a constant speed, so that means your effort will be equal to the weight. Do you agree? So the work done by gravity is going to be negative. Okay, because gravity in that case, when you are lifting, is doing work against you. So what will be the net work? Zero. You are moving at a constant speed. The work that you are doing on it is being taken away by gravity. So that will be the work done by you. That will be the work done by gravity. So the net work will be zero. Because if something is moving at a constant speed, that means up equals down. Okay? Thank you. Agree? What about if you're going down? Gravity is doing positive work or negative work? Gravity is trying to spinning it up, slowing it down. Speed up. So it's doing positive work. And when you are going down, you are doing negative work. Oh, now I'm tired. But the net work is going to be zero. Agree? So the network is zero as long as there is a constant speed. That was exhausting. Okay, so we say that gravity is a conservative force. And because if you move a mass, so here I have a mass from that point to this point, what's going to be the increase in potential energy? mgh, right? So it depends only on the height. Now, if I go from here, boom, 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 I go walk over there and I come back there, it's still going to be mgh. So it means it doesn't depend on the path. Potential energy is always equals to mgh. So it depends only on the initial position and the final position. So typical question on the test. I go from here. Okay, so you have a height here, and I go boom, 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 and I come there. What will be the change in potential energy? They both have the same height. So the potential energy, it's going to be the same. So the change in potential energy will be zero. Okay? If there is no difference in height, there is no difference in potential energy. So from this position to that position, the potential energy, the difference in potential energy will be mgh. But it doesn't matter if I go straight from here to there, or if I go up and take a walk and go back there. The change in potential energy will be the same. So let me ask you something. Typical conceptual question as well. So you have a right here. So you go tulululu, you go loopy loop here, and you go this way, and you go that way, and you come back to the same place. What's going to be the change in potential energy? Zero. Very good, because you go back to the same height. There is no difference in height. There is no change in potential energy. And that always happens when you have what is called a restoring force. So it means a force that wants to bring back the system to a lower level of energy. Thank you. Yeah. Okay, so now the work done by friction is always negative. So, like typical, thank you. So I'm going to try to trick you. Let's say you do a loopy loop, right? So there is a ride. So this is a circle and it has a radius r. So the distance around it's going to be 2 pi r. Okay? And let's say it's something here moving along the track and coming back here. What's going to be the change in potential energy if you go back to the same place? Zero. Do you all agree? Mm-hmm. But what about if you have friction now? So you see, the friction is always along the path. So this, I don't know if you see, but that's a cart or something moving along that path. And let's say you have kinetic friction. All that energy that will be lost along the track, it's going to go into heat, right? Or noise. For example, you are making noise as you go along. You cannot get it back. Do you agree? Mm-hmm. It's going to be lost forever. So what do you think is going to be the work done by friction? So the work done by friction will be equals to, so let's say the force is the same. It's going to be negative times what? The circumference, 2 pi r. So typical conceptual question. The work done by gravity will be equals to 0. Okay, because there is no change in potential energy. You go back to the same place. But the work done by friction, it's force times the distance covered, because of course it's going to be depending on the distance here, right? If you have a larger loop, you're going to lose even more energy, you're going to produce more heat. Does it make sense? Mm-hmm. So if you are pushing a crate and you are not sure, maybe I should go this way and maybe I should go that way and then go this way, the work done by friction will be equals to friction times that distance here, because along that path you're going to lose energy to heat. Is that clear? Mm-hmm. Okay, and then we get to the work-kinetic energy theorem, which is very easy to understand. The net work done on a system equals to the change in kinetic energy. So if there is work done on the system, the speed will increase or decrease. Thank you. Okay, let's try to do that. You're on your own, okay? Don't say anything. Do it. Work. Help each other. Just apply. the definition. Work is force times distance. That's all. Work is force times distance. If the work is negative, that means energy is lost. And if the work is done by friction, you need to multiply by the distance. Okay, so do it. Okay, so what is the work done by you on the box? You just multiply the force, and the distance is 5 meters. 500. So 100 times 5 is 500 joules. But you have kinetic friction, so the work done by friction on the box, it's gonna be minus 50 times 5. Negative 250. Yes, negative 250. So when you check your account, $500 in, $250 out. So what will be the net energy transfer to the box? It's going to be positive. It's better than negative, right? So the box will have an increase of energy of 250 joules. Okay, it's an increase. It's like a deposit. Okay, and then the kinetic work theorem says that if there is a net work done on a system, then there will be an increase in kinetic energy. So it's going to move faster. So what's going to be the increase in kinetic energy? By definition, it's going to be the same, right? 250 joules. Agree? Okay, so try to answer. Don't space out. Already I see people, they sign in and then they leave. Like I don't see them. So don't space out, okay? So the network will be equals to the change in kinetic energy. And by definition, I mean, not by definition, but what is the change in kinetic energy is 0.5 the mass, final speed square minus initial speed square. And initial speed is 0. And they want you to find the final speed. And do we have the mass? Yes, we have the mass. So try to do it. We kind of already knew that, right? If there is a net force, there is an acceleration. If there is an acceleration, that means that the speed will increase. So we already know that. Okay, so do it. So 250 equals 0.5. What's the mass? 50, thank you. What's the final velocity? That's what I want to find. Square minus initial is 0. So 250 equals half of 50 is 25. And then final speed. So final speed square equals 10. Yeah. And so the square of 10 is what? 3.2? Okay. I just want to go back because I'm not sure if it was clear. So I want to go back to this idea. So the change in potential energy is mg, okay? The change in height. Do you agree? And that will be also equals to the work done by gravity. So for example, if you lift something, you are doing work against gravity. That's why we have strong bones. That's why I feel bad for the astronauts that will be stuck until February because they don't have gravity to work against. And so anyway, the work done by gravity will be mg, okay, and the difference in height. So if you go this way, and you come back, what will be the work done by gravity? It's going to be 0 because you come back to the same place. However, when you're going to have friction, you see friction is this way, okay, and you have your little train. I don't know, it's like looks like a train here. So frictional force is doing negative work. So the work done by the friction, okay, on the train, okay, will be negative. That will be the kinetic force times the total distance. I want to make sure that this is clear. So you will have to find the distance here. You can use like a meter tape. Okay, you find the whole distance here. You multiply the kinetic friction, which is about constant because it depends on the material in contact and the normal force times the total distance. So if you go back to the same place, the work done by gravity will be equals to 0, but the work done by friction is not 0. So that's why gravity is called a conservative force, it's just a terminology, and the frictional force is called a non-conservative force. Because you cannot get back, like it's lost. You cannot get the heat back. It's lost to not only to heat but to noise, scratching noise, and maybe like some spark. Is that clear?
Yeah.
So what makes us strong is doing work against gravity. Okay, we did well today. If you have any question, let me know. And remember, for test number 3, I'm going to extend the time to accommodate everyone, but the test should be like an hour and a half maximum. You're not going to stay in front of your computer for 5 hours, right? I'm just extending it to accommodate everyone. So no, don't send emails to the DRC. It's no use.